Hello and welcome to this instructional video on the Incident Energy Calculator, which is among a suite of 10 tools that are designed to allow a competent electrical engineer to determine the severity of an arc flash incident. My name is Mike Frayne and I'm the creator of the European Arc Guide and the author of the book The European Arc Flash Guide. To understand the risks of the arc flash hazard, you need to be able to calculate the incident energy level at the worker. Prediction is fundamental to the whole risk assessment approach because, as they say, if you can't measure it, you can't manage it. In using these hazard severity tools to calculate the incident energy at the point of work, this will provide the bedrock of information from which decisions can be made in respect of safely managing the risk. Once you can identify and quantify the hazard, you can decide if work can proceed and if so, what preventative or protective measures need to be in place. Once this is completed, you can continue to manage the risk by using the Prevent, Process and Protect chapters from the guidebook shown here. To access the Incident Energy Calculator, select the Calculators tab and then Incident Energy. If you select Expand or Collapse, you'll be able to provide preset configurations which will reduce the need for repeated data entry where the same conditions are being used in several calculations. The second option is to click on Incident Energy Calculator Instructions, and this will give you access to comprehensive guidance on how to use a calculator. Back to the main dashboard, we can start to enter data. The first field is Equipment Classes. This gives you a choice of several classes of equipment which will provide you with suggested enclosure dimensions and conductor gaps, which is from IEEE 1584. As you can see, if I select low voltage switchgear, the greyed out boxes are all pre-populated with this information. Alternatively, select manual entry for the drop-down menu and enter bespoke data. In this case, we'll choose manual entry. The next field is electrode configuration, and you can learn all about the configurations from the instructions and a more detailed account in the guidebook. As can be seen in this diagram, the configurations are VCB, VCBB, HCB, VOA and HOA, and basically denote vertical or horizontal conductors in air or constrained in a box, the odd one out being VCBB, which is vertical conductors that are terminated into an insulating barrier within an enclosure or box. We'll use VCB for our example. The next field is a system three-phase line voltage, and we're going to use 400 volts, which is a usual LV system distribution voltage commonly used in Europe. Next is the prospective short circuit fault current at the equipment terminals, and that will be required in this case. Please read the guide to make sure that you don't fall into the trap of putting forward an unrealistically high fault current at this stage. Paradoxically, a low fault current value can result in a high incident energy level due to increased disconnection time. There is a prospective short circuit current calculator available with the ARC guide. Next, we have the conductor gap distance, which may be the distance between bus bars, equipment terminals, or alternatively cable conductors. We choose manual entry earlier, so we'll figure that we'll use 32mm in this case. Next we have the working distance, which can vary with the task to be performed, but in this case the figure is going to be 450mm, which is a reasonable working distance for testing and fault finding. There's much information about distance in the guide, as the relationship between distance and severity is exponential, meaning large changes in incident energy can occur for very small changes in distance. The next three fields are the enclosure dimensions, and as we've selected manual entry, the bespoke dimensions can be entered here. Any of the other equipment classes will result in automatic data entry. This stage will go with the figures given here. You can see here that there's also an option for the inclusion of motor contribution at the equipment, and this is covered in detail in the instructions and the guide. If we press the submit button, then you'll note that there are two arcing current values, IARC on the left and a reduced arcing current IARC min on the right hand side. The reduced arcing current gives a further level of confidence to see if it has an effect on the operating time and consequently the incident energy due to system variations. From these two calculated arcing currents, a corresponding time for the upstream protective device to operate can be obtained from its time current characteristic. There are tools provided with the guide that will assist you, such as the IDMTL calculator and also the time current curve tool, both of which give a direct time output. This is entered into the corresponding fields shown, and in this case we've determined this to be 0.5 seconds for IARC and 0.55 seconds for IARC min. Press the submit button again, and the final incident energy level is shown for the higher level of arcing current. If we increase the disconnection time to 0.6, shown here, for the reduced arcing current IARC min, the higher level of incident energy will be shown for this reduced arcing current. In addition to reporting incident energy, the calculator will provide the arc flash boundary figure. This is a distance from an arcing source where the incident energy level falls to 1.2 calories per square centimetre. Finally, the result can be stored by pressing the Store Incident Energy button at the bottom here, and the result can be exported, printed or used in a dynamic risk assessment, for that is provided with this guide. As a brief glimpse of the form, we can click on Calculators, and there's an option, as can be seen, for Risk Assessment. Click here and this opens a form which, as you can see, is sectionalised for Predict, Prevent, Process and Protect. This dynamic risk assessment checklist form will allow the user to systematically go through the 4P steps and consider the actions one by one. You can either complete the form online or download a Word document which can be custom edited for your own needs. I do hope finally that you enjoy using the calculator in the field, perhaps on your phone or tablet or PC, and that you find that this guide to be a valuable resource to discover and manage dangerous levels of incident energy in the workplace, and therefore ensure the safety of electrical workers. Thank you for your time.